Further ado, I'm introducing Xeno, who is reverse engineering Bluetooth chips to make better Bluetooth security tools and classes. Take it away.
Thank you. All right, hello everyone. I have 145 slides, so I'm going to be going a little fast. So I'm Xeno. The majority of my time is spent on my nonprofit open security training, where we create and give away free classes that are the same high quality classes you would pay thousands of dollars for. So go take our free thousands of dollar classes. 25% of my time I do consulting and research, and that's just for funsies, and that's also just a Trojan horse to get things like open security training in front of you to say, that's what I really care about, making everyone better. So, Alakazam, boom, all of a sudden these dongles can send packets that architecturally in Bluetooth specification, you are not supposed to be able to have full control of these packets. They don't want you to send these packets, but I want you to. So, that's what I made possible. So how you do that? Well, you go off and run a couple of sudo copy commands on your Linux system, or you run my install dark firmware real.sh, and therefore you put a custom firmware onto the box, and then you plug in a USB dongle, and that is now running custom firmware. So it's about as easy as I can make things on a Linux box. So this is going to be Magic's biggest secrets revealed. I wanted to talk to you all about how this worked and how I did it. But there's what I wanted to teach you, and there's what I need to do with my limited time. So what I wanted to present was like the literal timeline of going through of like, here's how you start, here's how you look at things, here's how you overcome the obstacles. And I started doing that. I started writing this talk in that form, and I got to 350 slides, and I said, this is probably not going to fit in 50 minutes, so I need to stop, redo. We're going to just focus instead on a little bit of the suffering, and we're going to emphasize for you that suffering builds strength. I hope all of you suffer in your lives, because if you don't, you're going to be weak. So go out there and suffer to build your strength. And we're going to talk about my suffering in this particular talk, because it was painful. So for this talk, we're going to have terminology of BT or BTC, or sorry, BC or BTC. Bluetooth Classic, not Bitcoin. So Bluetooth Classic, that's the original Bluetooth at circa 2001. Bluetooth Low Energy, BLE, that's the updated version of Bluetooth, circa 2014, 13, somewhere around there. And BD-Adder. BD-Adder is Bluetooth address. That's going to be mattering because some of my goals are focused on BD-Adders. So Bluetooth Low Energy has 4 types of BD-Adders. The first one is called a public address. And this looks basically the same as the MAC address that you know and love from Ethernet. And it behaves the same way as the MAC address you know and love from Ethernet. It's got a IEEE organizationally unique identifier, 24 bits at the top, 3 bytes. And that's going to essentially tell you this has to do with this company. So this will be Texas Instruments or Realtek. And then the other lower 24 bits are going to be just random values for any given device. Now, for what it's worth, the Bluetooth Low Energy public address will be equivalent to a Bluetooth Classic address for the purposes of this talk. Like basically, Bluetooth Low Energy has 4 address types, Bluetooth Classic only had 1, and that has to do with the idea that Bluetooth Low Energy introduced the idea of we don't want people to be trackable based on their Bluetooth device addresses, which they're spamming out all the time. And consequently, Bluetooth Low Energy added these sort of randomized addresses to make you less trackable. But they still have this old form that Bluetooth Classic used. Now, what matters for the purpose of this talk about BD-Adders is that Bluetooth Low Energy, it is easy to spoof those addresses. If you think of like Wi-Fi and what you have to do to spoof addresses, maybe it's easy there. Ethernet, easy. But specifically, architecturally, it's easy. There is a spec'd out way to change these 3 types of addresses. Just send an official command, you get to change the address. There is no spec'd out way to change public addresses in Bluetooth Low Energy or classic addresses in Bluetooth Classic, which means that if you want to do that, you're going to have to do something non-standard. So my motivation for this talk, I've got many motivations, and so the first motivation is that in the future open security training Bluetooth 1501 class that my wife Veronica and I are working on, we want to show machine-in-the-middle attacks specifically against Bluetooth. And we want to do that using WAD. WAD is the Wireless Hacking Toolkit that was released a couple years ago at DEF CON. But again, there's no architectural way to set public addresses. So if you want to machine in the middle a device that is speaking with a Bluetooth Low Energy public address or Bluetooth Classic address, then there's no official way to do that. So these days, we use these CSR4 dongles, and they're called CSR4 because 1, they're using Cambridge Silicon Radio, CSR silicon, And 4.0, because they have the Bluetooth 4.0 spec, is the only thing this silicon supports. We are now, as of August or something, on the Bluetooth 6 spec. So this is super old spec, which means it doesn't support a bunch of packet types. But yet, Bluetooth researchers, ourselves included, because no one wants to go out and do the work until today, no one wants to do the work, so we're all stuck using old garbage hardware. So 2010 is what we can do in terms of packet types, and that's bad. So we want to teach Bluetooth spec 5.4, which is what we built our class around, so we need to go out and find some hardware that lets us send custom packets for guaranteeing machine-in-the-middle capabilities in the future. I have an additional motivation for this talk, and that is that for the last couple of years, basically my wife Veronica did a talk at Black Hat 2020 where she found over-the-air arbitrary code execution vulnerabilities in Bluetooth for Texas Instruments and Silicon Labs silicon. So send a magic Bluetooth packet, get arbitrary code execution in the silicon over the air. So she did that in 2020, but basically we couldn't make a big hairy deal about it because we didn't know where all that applied. We don't know which chips have Silicon Labs, which devices have Silicon Labs, which devices have Texas Instruments. So ever since then, I've been doing this thing called Bluetooth printing behind the scenes where I'm running these sniffers and analyzers and active fingerprinters, tooth printers, where I'm sending out all of this information to your Bluetooth devices to get more information about what kind of hardware they have. So I've been doing that for a while, and there's one particular tool I used as a part of that. It's called Bracktooth. It's some other public research tool that's been created by academics, and that can send LMP. This is the lowest level link manager protocol, the lowest level Bluetooth classic packet type. It's a type that you can send and receive, having nothing to do with pairing and that high-level stuff that you think of when you think of Bluetooth or talking. I need to put in a 4-digit PIN code. No, LMP packets are sent around down at the lowest layers, having nothing to do with that sort of authentication. So pre-authentication, potential vulnerabilities, and data collection. So I've been using Bracktooth, but Bracktooth, I don't want to say it sucks, but it is suboptimal. It is suboptimal in the sense that at the time it was released, it only supported, it is not open source, it's still not open source. It only supported x86 64, so I had to run these boxes that are like little mini x86 boxes, which means it's high power consumption. I have to throw a voltage converter. It's not meant to run off USB, it's meant to run off being plugged into the wall. The box itself for Bracktooth is using an Espressif dev board that's big and fat, so suboptimal. Beyond that, the Espressif dev board that I have to use, you can't even buy anymore. So like officially supported board, can't even buy it. Had to go find new boards that still support Bracktooth. But this is the comparison here. This is what I have to use today. This is what I want to use. I just want to use a little USB dongle. I want to have a discrete antenna so that I'm not using a PCB antenna with limited range and power and everything else. So that's where I'm trying to go for upgrades. Furthermore, for Bluetooth printing and putting this out there for other researchers to use, the Espressif kit is $55. That's comparatively expensive to these cheap little USB dongles. You can get them as cheap as $4. I've gotten them for $4, but then they don't have the full antenna. So let's call it $15. I want to decrease the price for people to work in this space. That means not forcing you to buy a $300 x86 box, and that means also using small cheap dongles. So one of these things is not like the other, and I don't like that. And then finally, the motivation 3 is leading by example. So basically, as part of the Bluetooth printing class that I've already published for open security training, as part of the future open security training class on Bluetooth Low Energy, I'm trying to put together a crew. So anyone who's interested in Bluetooth security and hacking all of these thousands of devices that are around us that you don't see, well, I'm putting together a crew for people who want to do this. I'm providing mentorship and guidance, and this research is basically saying, dear crew, here's how I reverse engineered one particular chip. There are 20 other silicon vendors that we need looking at. Go forth, do the same thing, do another talk. So this is kind of guidance for future talks. So let's see if that Zoom works. Oh no, that's going to be terrible that doesn't work. All right, so this is just to give you a sense of open security training, learning paths and stuff. We've got the Bluetooth printing class already published, but there's going to be classes on Bluetooth Low Energy, and then there'll also be classes on Bluetooth packet crafting and classes on vulnerability hunting, which tie into our existing vulnerability hunting classes. So basically, you can learn all sorts of awesome stuff in the future. But it's time for me. So talk about the suffering and strength here. Just a little hint of the suffering here is the chip that I'm looking at is going to be a MIPS 16E based chip. It's not well supported by Ghidra. I have to work around that. There's no public or private SDKs. I can't just go off and look at example code that they have. There's no good leaked documentation to tell me about the internals. There's no strings in the ROM, or almost no strings. There's just enough strings to be helpful. There's no JTAG option. And yeah, basically I have to end up, want to run a custom firmware, go off and hand code some assembly, right? So this research started about a year ago where we had this notion that like we're making a class, using CSR dongles is bad because it doesn't support the latest and greatest packets. We need something, we're going to need to replace this at some point. So what I did is I go to Amazon and I just go buy some cheap USB dongles that say ostensibly they support Bluetooth 5.3, 5.4 in the general range for our actual class teaching material. So they say they support 5.4 directly on the box, but when you go and plug them into Linux and you run HCI config-A, what you see is that Linux reports them as, yes, this is Realtek, but no, this is not 5.3, not 5.4, this is 5.1. And indeed, I've confirmed that with Realtek themselves. This particular silicon in this particular dongle only supports Bluetooth 5.1. Basically, there's a whole bunch of like white label Chinese dongle makers who are selling this under false pretenses, just straight up lying. So they're saying this is the latest and greatest version. I'm sure they'll start saying 6.0 support soon. So, like, you have to figure out what's going on here. We said that the key thing is, like, all those cheap dongles I bought off of Amazon, they are all running Realtek chips. So, essentially, we can say someone somewhere in the supply chain is widely distributing. These must be really cheap to make things based on and spin up a new white label thing. Zex MTE has disappeared now, and there's a new version of it. So I can't remember their name. But the point is, what I should have done early in this research, which I didn't do until much later to take these pictures, is I should have cracked them open and taken a better look at the internals. So here we have one of them that has the RTL8761B UE and one of them that's BUV. So two equivalent things. I really expected these to be true white label and see the exact same circuit board, but no, they were different circuit boards and indeed different chips. So what I should have done was crack it open. What I should have done is go and read the specs carefully and see, okay, the BUV and the BUE, these both have USB interfaces, but there are two other things here, the BTE and the BTV, and these have UART interfaces. So why that matters is around April, I decided to get serious about this and said, okay, I think I'm going to want to look at Realtek at some point in the future. Let me go buy a dev board, because your best option always when doing this kind of research is buy a dev board. You can usually either directly officially put on custom firmware, or you can use an SDK or something like that. Now that works for other chips which are meant to run third-party code, but it turns out these are not really meant to run third-party code. These are just meant to run Realtek's code, and consequently they don't have that sort of support. But still, I went out, I bought a built board. It turned out to be a BTV board. I got confused by the fact that I'm sitting here looking at this picture and saying, oh, it's got a USB port on it. That must be the USB dongle dev board that they're selling. No, it wasn't. It turns out that has the UART interface. This only interacts via UART. They have a different USB board off to the side that is the USB interface one. So if I had bought that, then I could have plugged it in and interacted with it exactly the same as USB dongles, but I bought the wrong thing. So first bit of suffering, do as I say, not as I do. Make sure you always double check the chips when you're buying your dev boards. Yeah, just do that. Okay, so the actual start of this project didn't really start until last July, basically when I was running the Bluetooth printing class. I don't have to spend my full time and attention with the beta testers. I just start the class, do a beta test, let them ask questions, and behind the scenes I was like, okay, let's go ahead and do this research now. So first thing I do, try to power on the dev board, finally in July, and no dice. It is not powering on. There is zero interaction via USB, zero interaction over UART. So at this point, I think I'm being scammed, and basically I'm messaging the Alibaba sellers, which only official place you could buy these at the time was Alibaba, and I think they're just scamming me and and stuff. I ping them, and they say, look, we're just shipping whatever Realtek gives to us. Take it up with Realtek. And indeed, it was not their fault. It was Realtek shipping these things wrong. So while I'm waiting on this, I ping Realtek, I ping Alibaba, while I'm looking at this, the next thing one might do is one might look for firmware. Where does firmware exist for this chip, and how can I go analyze that? Usually you might have firmware updates that are downloadable components, and you might go off and look for those. Now these were nice because there is firmware just baked into most any Linux distribution. If the Linux distribution intends to use Bluetooth USB, and for the Realtek, it's going to be baked into /lib firmware RTL-BT. And then they've got one for the B and the BU, and that turns out to be the UART and the USB interfaces. So this is the paths where they are in Ubuntu 24.04, and the same path at earlier OS is just without the Z standard compression. So what I want to say at this point is that then I did, another thing you as a researcher should do is survey, right? Don't reinvent the wheel. Go search extensively for what has been done in this space and, build on any existing research. You do something new and unique and novel. Don't reinvent the wheel. Very important for people who are going to do this for other chips. So there is no Bluetooth Realtek research, like straight up zero research whatsoever. There is a little bit of Realtek Wi-Fi research, but when I say a little bit, I want to say order of magnitude like 3 talks maybe. But the thing is, oftentimes, interestingly, Bluetooth and Wi-Fi cores, Bluetooth and Wi-Fi chips, will either be a single chip that has like multiple cores inside of it, one of which is doing Bluetooth, one of which is Wi-Fi, or multiple chips together. So Wi-Fi and Bluetooth are joined at the hip, of course, because they're both 2.4 gigahertz protocols, and therefore they're going to be sharing antennas. They're both speaking commonly over the same 2.4 gigahertz antenna. They have a notion of coexistence. Bluetooth and Wi-Fi need to play nice with each other. So there's a person called 8051 Enthusiast who really likes looking at chips based on Intel 8051, and he had done some analysis of a Realtek Wi-Fi Bluetooth combo chip. The Wi-Fi side of it was an 8051, so it was in scope for him to go reverse engineer and find that. But while he was there, he gave me the barest of hints to say, like, he looked at the Bluetooth core that was off the side, didn't look like 8051, didn't really care, but he was thorough, and he said, okay, I see a repeating pattern of 00665, and he thought, okay, maybe the repeating pattern is no-ops, and he did a bunch of analysis that I don't have time to talk about to basically say, yes, indeed, these are no-ops, these are used as padding for different compilations, and they are MIPS 16E. So that was the hint that I needed to start doing something useful in Ghidra. So MIPS 16E is a short-form encoding of MIPS, just like thumb is to ARM. So thumb is like 16-bit encoding for ARM. This is 16-bit encoding of 32-bit MIPS instructions. Now that's a problem because I don't know MIPS. Who here knows MIPS? All right, cool, we got some people who do know MIPS. Well, I don't know MIPS, but look is what happens when preparation meets opportunity. So basically, I got lucky here because I know RISC-V, because I teach a RISC-V class at OST2. I had no reason to teach this class except to force me to go learn RISC-V because I thought it was cool and I thought it would be something future interesting. So I teach RISC-V, and it turns out that the MIPS opcodes very significantly overlap with RISC-V. You can think of it like, in some sense, MIPS is like RISC-3. Basically there's a whole RISC family tree stretching back to the Berkeley and their RISC architecture. And so MIPS is like RISC-3-ish type thing, or RISC-2, I don't know. But RISC-V is of the same genealogy, and therefore the instructions are basically the same. So even if Ghidra's decompiler didn't work, which thankfully it did work, but even if it didn't work, I could still at least read the raw assembly. So this is, again, just my avocation, my backdoor of talking about open security training. Basically, you want to get lucky, get prepared. You never know when one of these classes that we're giving you for free is going to be the thing you need for your research. So even though Ghidra does disassembly for MIPS 16E, it's not particularly well supported. So now we have to start working around some things. First of all, you have to go off and select the MIPS 32-bit little endian thing. And what I hadn't noticed to start with there is that it says MIPS 16E as well. And so you go there, you look at this start of this file. This is the Linux file. This is this Linux Realtek Bluetooth firmware sitting in the firmware folder somewhere in Linux. And you look at it, you've got some header stuff. It says Realtek. I would zoom if I could. Let me try that again if it doesn't. Nope, no work. Oh yeah, and by the way, again, AV people, get rid of the picture-in-picture. Then you have a bunch of zeros. So a bunch of zeros, but within this headerish type stuff, there is a location that has like a 30 and a 3780, which kind of are maybe thought of as pointers. AV people, get rid of the picture-in-picture, please. Yes, it's going to cover up stuff in a second that really matters. Okay. So you get a bunch of zeros. The zeros ends at 30, and then here at 30, we now have some non-zero stuff. And the non-zero stuff is what we might assume is going to be assembly. And so you do what you normally do. You hit D, you disassemble it, and you get a whole bunch of nothing there. You get instruction daddy. And so what you actually have to do in Ghidra is you have to use F12 in order to disassemble specifically as MIPS 16E, and then you're going to get a whole bunch of valid code, and then you can hit F to turn it into a function. But the problem becomes When you're encoding stuff in 16 bits, you can't possibly be referencing like 32-bit addresses. And so that means that functions that want to, like, say, there's an address of stuff here, instructions have to say, no, actually, there's like some data a little bit later on, and I want to reference that data. So basically, code followed immediately by data, and Ghidra didn't like that, and Ghidra basically says, I will do one function worth of disassembly, and then I will stop because, I don't know, point. So basically, we get this recurring pattern where code, data, failure to disassemble, code, data, failure to disassemble, right? So what do? You file a Ghidra ticket, and now you play the waiting game. But the waiting game sucks, and so instead I was going to have Veronica make a script for me. So for anyone out there in the audience who doesn't want to go off and learn scripting languages for IDA or Ghidra or anything like that, I highly recommend having a former NSA capability development specialist in your house who you can just throw work to as necessary and say, can you please write me a script so I can disassemble properly? And indeed, she did that, and great. Now we've got like a whole bunch of disassembled code that we can start doing decompilation on as well. Great, more disassembly, more better, but there's no string still. And of course, we know that reverse engineers really, really want strings in order to make sense of stuff. And the absence of strings does not bode well. So at this point, you start doing some open source intelligence. You scrape all the Realtek documents for all the chips, even if they're not this chip. Maybe they give you a hint of something that's useful. And so I download all the possible software, and eventually what I did is I came to the conclusion that this chip is using what are called vendor-specific commands in order to interact with its firmware. So this is our big picture of like, here's everything. Oh, interesting. I didn't even know my mouse wasn't showing up this far. Sorry about that. That's going to be hard to deal with. So basically, this is our big old stack of the entire Bluetooth thing. Now, we have the host side and we have a controller side. I want you to think that the host is essentially Linux, and the controller is essentially the Bluetooth chip. It's the Realtek chip. So hosts are operating systems. They don't need to be in different embedded systems. They'll have different architectures. But for our purposes, let's assume it's Linux interacting with a Realtek chip. And so basically how Linux can do things normally is we're going to merge, like Linux supports both Bluetooth Low Energy and Bluetooth Classic, so that is the Linux host. This particular Realtek chip supports both Bluetooth Low Energy and Classic. That need not necessarily be the case. Like if you ever see a Nordic chip, Nordic only supports Low Energy, they will not support Bluetooth Classic. So Linux normally will send what are called host controller commands, so host controller interface commands. And so those are spec'd out in the Bluetooth spec, and so you can have things like set random address. That's the thing that I said is an official way for you to spoof a random address and be able to control the BD adder of a dongle, or a Bluetooth Classic-y type thing like inquiry. Inquiry is how you like discover the other devices that are out there. And so the Bluetooth controller knows these. The Bluetooth controller has these low-level packets down here. Now, I forget whether I say this elsewhere in the talk, so I'm going to just say it now. The key thing about this host controller interface, it's good and it's bad. It's good because if you compare this architecturally to other things like Ethernet chips, Wi-Fi chips, stuff like that, they have spec'd out an official interface from the main x86 processor, ARM processor, down to the chip. There's an official interface that chips can implement the particular commands, and then this is like abstracted away. So that's nice. There's an abstraction layer here instead of being like vendor-specific interfaces using vendor-specific kernel drivers, which is what you get in like Wi-Fi Ethernet world. But what this means for us as researchers who want to control everything everywhere is that the lowest level of the Bluetooth protocol stack, link layer control protocol and link manager protocol in Bluetooth Classic, these are out of our control. Like we can't fiddle with anything in the operating system and send arbitrary packets down at this layer. We have to go fiddle down in the firmware layer of a Bluetooth controller if we want to take full control of these packets. So Realtek then, and all other vendors, they will have what are called vendor-specific commands that transit this host controller interface, and those can do whatever they want. So anything custom that they want to do, any sort of diagnostics, any sort of information collection, any sort of firmware update, these are typically done still by a vendor-specific command. It's not like a vendor-specific kernel driver, it's now just officially supported vendor-specific commands with have unofficially, whatever, do whatever you want kind of thing. So basically, what we can do by just observing what's going on this device is we can have a sense that there's going to be some ROM, there's going to be some RAM, and so any firmware update must necessarily land in RAM. And consequently, what we see by just using the built-in what's called BTMON tool, Bluetooth monitor tool. It's a built-in thing for monitoring the information transiting the host controller interface. We can see that they're slicing up their firmware and they're sending it down to the chip, landing presumably in RAM somewhere, one little 253-byte fragment at a time, using this vendor-specific command, which has opcode command field 20. So also, let me go back to that picture for a second, there's the firmware, and then there's also a config file after it. So right there at the very end, the orange stuff, config file is going to be tacked on the end. So what are the config files? Well, when we look at documentation for the config files, we see that they control a bunch of things like setting UART baud rate and stuff like that, but the most important thing to me is it allows setting the BD adder. So from the scraped public documentation of all the other chips, I know that Realtek architecturally uses config files to set BD adders on other chips. I just used their existing config files. They didn't work on this chip, so I can't just use it as is. But I now have a hint of where I want to go if I want to spoof the BD adder so that I can do the machine in the middle attacks so that I can teach people about that in the OSD2 class. The format of those particular, we're going to call them packets, transiting from the host to the controller, is that you've got 10 bits at the beginning of the packet, which is the opcode command field. This is literally just the command you want to do. And then we have 6 bits of the opcode group field. So there's going to be grouping of different commands, the Bluetooth low energy commands, some Bluetooth classic commands, and so that's what grouping means in this context. Now that's super annoying to look at because you've got a 10-6 split, so it's not just like 8-8 and you can just read a byte. And so what you have to think of when you're doing reverse engineering, again, this is our hints for future reverse engineers doing Bluetooth reverse engineering of firmware. What you have to think of is that vendor-specific commands always have an opcode group field of 3F. That's just the reserved value for it. And so 3F shifted up by 10 bits is going to mean that we're going to have this 16-bit field as something that either starts with FC, FD, FE, or FF. Basically, just the most significant 6 bits is equal to 1. So those are the things we keep our eyes out for as we're reverse engineering things. If we see 3F, if we see FC through FF, if we see shifts by 10 bits, this indicates that we're looking at some sonic code that's like consuming, on the controller side, consuming these HCI commands. So always let the specification be your guide because basically you need to use things like specs in order to give yourself hints when you're just looking at a bunch of non-stringed out assembly. So eventually on the 8th, on the August 1st, Realtek sends me some commands and PDF instructions for how to start this thing. Theoretically, I should have been able to figure it out. Like literally, I had started like using a continuity tester and like just seeing what's connected to what, but I really didn't want to fry my boards and wait another 3 weeks to get them shipped from China. So basically, I waited, and here you go. There you go. It's not proprietary. They should have shipped it this way. That's how you power your own boards if you go off and buy one of them. Great, it powers on, now what? I already said I bought the wrong board. It doesn't do anything over USB. It uses the UART interface. So we've got a UART interface down here at the bottom of the board. Hook that up to your USB to UART adapter, and then plug that in, look at it either on a logic analyzer. You plug it in and it does nothing like a USB dongle, and so, okay, now you have to throw it into a logic analyzer, and it also does nothing. And so where do you go from here? Well, you keep doing your open source intelligence, right? So you just keep Googling around, searching in, hopefully not in vain, for information that can help you. So that's what I was at. I was basically just dead end. I don't know what I can do with UART. So what I did was I started poking around with the various tools for other chips that I had scraped from Realtek's public information. There was one particular tool called RF Test Tool, which I could see based on the UI had an ability to connect to some COM port. So basically a UART port, a serial port on Windows, connect to a COM port and do stuff. And some of the stuff is useful stuff like reading the BD adder. That at least tells me connect to UART, read BD adder. That's probably doing something via HCI, but that's an official HCI thing. That's not like a vendor-specific command. So I'm hunting for vendor-specific commands to do the custom stuff, and there's a nice little hidden menu, not hidden, but just you enable this little BT menu right there. And what you get from that is this interface, which has a thing called BT RW Reg, which sounds like BT, Bluetooth read-write registers type stuff. And it's got like a thing called RF, which we might infer is like radio frequency registers, modem frequency, BT SOC Aon, maybe Bluetooth system on a chip, always on power domain. So there's stuff here we can play with, and there's addresses, and there's reads and writes, right? So cool, I stick in addresses like 0, and I read and I write and I see zeros. Here's where I would have zoomed, but the zoom's not working there. Actually, if I do this, does that work? Oh, sweet. Okay, cool. So a bunch of zeros, a bunch of not useful, right? That doesn't tell me that this tool does anything useful on my system. So a Ghidra hint at this point is that one of the super useful things is this element called defined data. So there is a defined data window, and we can see a little bit of it right here. So I can see a whole bunch of addresses that are defined. The thing right here is that Ghidra will show you in the assembly, like if it's blue, that means it's a reference to a data address that is within the scope of the stuff I've got loaded in Ghidra right now. If it's red, it's a reference to a data address 8010A02C that is not within the scope. So basically at this point in Ghidra, I've just got the firmware file from Linux dumped into Ghidra at offset 0. I didn't try to offset it any. I don't know where it should be offsetted to. But I can see, based on the disassembly of that it looks like it's going to be out there trying to, I don't know, load a word from offset 0, or load a word from that particular address. So that gives me a hint that this firmware is trying to read from that memory address at some point, and therefore that should be a valid address if I can just read from it. So go to the data addresses, just pick the last address in that big area, and then essentially use the tool, and we see something non-zero. So that's great. Non-zero something means the tool is doing something useful. If it's just always returning zeros, I think it's maybe the tool is not working, but non-zero means it's probably doing something. So next, what I want to do is specifically, then I have to actually figure out which of these things matter and which of these things may or may not be actually reading from memory versus reading from registers, as the name implies. And when I use that last one, what I see is this reference to read flash FC61. And that immediately looks great to me because I told you earlier when we're considering HCI commands, the upper 6 bits of the 16-bit value are going to make it so that we have FCs, FDs, FEs, and FFs. So that looks like something that might have to do with a vendor-specific command. It's in the right range, but I also know that this particular chip does not actually have flash. It's just straight up not having any flash. It's mostly running from ROM. So consequently, I have to figure out what is this actually doing behind the scenes? Now, had I given you the 350 slide version of this picture would make more sense. In some sense, it's unnecessarily complex right now. That is like the Windows Bluetooth architecture stack. You don't actually care about that. All I want to say is Realtek tool running somewhere up in user space has to talk somehow down to kernel space to talk to a COM port. The COM port is plugged into my little USB to serial adapter dongle, which is hooked up over UART to my dev board. But in the end game, I have to essentially connect this to a logic analyzer as well to actually log what is the tool doing. This is what I'm essentially getting at here. What is this tool from Realtek doing, and how do I figure it out, right? I can go reverse engineer the tool, but I know where the data is transiting. The data is transiting this link to my board, so go ahead and hook up a logic analyzer to that as well, route that into Sale's logic analyzer, and now we can actually see what's going on here. So when I run the tool itself and I read from this particular address, I get back this particular data. So all ones and some 0. And so this is why I needed the zoom here, because this is not going to make sense otherwise. Here's my logic analyzer trace. And what I'm seeing here is the data going from the x86 out to the Realtek dev board. And so what I see is the FC61 as bytes that are sent. And so that tells me it's sending the same thing it's printing out, and it's probably that vendor-specific command. Furthermore, I see 4 bytes saying this is the address to read. I put that into the tool, and that's the same data going out over the wire. And then I have a 20 here, which I don't know what it is, but I eventually infer that that's the number of bits to read, essentially. So it's reading hex 20 bits, 4 bytes. It's reading 4 bytes worth of data. And then if I look at, so this is the data going to the device, this is the data coming back from the device, and if I look at that, then I can say essentially, okay, exactly the data that the tool at the high level is telling me is coming back is what I see over the wire. So great, I can now say this device is sending vendor-specific commands, FC61, the read flash which on a device that doesn't have flash, but whatever read flash is, it's reading something from the device and it's sending me back some data. And I know some places that I might like to read because I've got a blob of firmware stuff, and I can see the references in assembly that says it's trying to read from 8010, blah, blah, blah. So I know ranges that I potentially want to read. I now have a capability to see like what commands do I need to send to read, and now I can start like reading those ranges. So again, super abbreviated form. Now we're going to do a game of map the memory, like figure out all of the RAM that is actually accessible in here, or ROM, right? We're reading memory addresses. We don't know if they're RAM or ROM. And so the nice thing here is that the memory controller sends you back dead beef if it's actually an invalid memory range. So we can separate out, like, is it sending us true zeros, or is it sending us, like, you're asking for something that's not real? Go away. So you just create a script that knows how to, basically talks to serial, sends these magic HCI byte sequences in the right form that we just reverse engineered from the logic analyzer, and you just scan all of the memory. And then you also have to make an alias detector because you see a bunch of stuff that is similar. So basically, like, this is what I come back with in terms of valid range, and again, that's why I don't want the picture-in-picture. Please stop putting it up there. All right, and so basically when you analyze it, what you're going to see is if you read from like all of the ranges everywhere, you're going to get some data that says it's the same data. And you can just automatically analyze that and say, okay, the same thing is coming back at the same 16 bytes, and you just try everything and you deduplicate, and you come up with something that looks roughly like this. We have what I'm going to assume is going to be a ROM, and we'll see why later. A ROM up at the 8 and all zeros. A RAM down at the 8, 0, 1 and all zeros. And these things are aliased. So the same ROM that shows up at 8 and all zeros also shows up at 8 and all zeros, and so forth. And then we've got some other ranges that I don't even still really know what they are. Future work, go do the reverse engineering. But I assume they're memory mapped I/O ranges. They are not really, touched that much. So, okay, I have now scraped all of the ROM, I have put it into Ghidra, and I still don't see any strings. So basically, going back here, I can read all of this, everything that is, non-empty here is a range that I have now scraped out and I've stuck into Ghidra and told Ghidra, disassemble it, run Veronica's script on it again. There's no strings, but I'm an optimist, so I go ahead and I do the manual string search. And it mostly gives me a whole bunch of junk, but within that junk, there is eventually some very promising things. And I want to say, like, out of the entire ROM, like, this is all the strings. Like, so we've got, 7 strings, whatever that is, but they are the strings that are of my interest. These are strings that are essentially saying something about HCI commands, something about HCI events. Commands are what go from the host to the controller. Events are what come from the controller back to the host. Something about LC, maybe link controller, something about LMP, well, that's definitely of interest to me. Link manager, protocol, lowest level stuff. And some mailbox that I still haven't explored either, which is maybe interesting. So go ahead, make them strings. And what do you do with those strings, right? You check the cross-references. So we've got a string like HCI command. You check the cross-references. That string is used exactly, 2 places. You go there to where the strings are actually used, and you take a closer look at that. And so what you see here is a bunch of references to the string HCI command, the string event, the string LMP. So these are all the interesting strings, all compacted down to a single function. That's nice. We've got some other references. We've got unique numbers on each of them. So the different strings like 3 versus 7 versus 4 versus 6. So maybe it's like just like registering something to deal with HCI events, registering something to deal with that. Maybe, maybe not. I don't know. What I do know is that basically these last bits in green are going to be some sort of pointer. So basically it's a data address. It's a memory address. And so inside this ROM code, presumed ROM code, there's a reference to some data. So let's follow one of those. We follow a memory address like that. Oops. Yep. So basically, if you were to, this is why I rely heavily on Zoom, if you were to take that particular address, 8021B60, you go look at that address, you see another address. So it's a pointer to a pointer. It's a double pointer. You see another address, and that address right there, 8200 to E11, whatever. You go there, and you find that looks like it's actually some code. So we've got a pointer to code that has something to do with HCI commands, and so we might infer that this is maybe command processing. So we might infer that, but we need some evidence, and what our evidence is, obviously I can give you a bunch more evidence, but what it comes down to is one of the inputs to this function. We can see it being referenced with respect to, is it 3, is it not 4, is it 8, is it 6, is it 3F? 3F again was one of my, your eyes should be blinking. 3F is the magic vendor-specific command thing. So I've got a function that I think is HCI command handling, and I see it using 3F, probably the firmware function that actually receives these vendor-specific commands, and then, oh, hey, there's a function right there that goes along with that. So if the input value is 3F, call this function. It's probably the vendor-specific command handling function. But yeah, this is why we always let the specification be our guide, because it turns